Same query, same parquet files, same 20 cores, and a table of 1,000 rows. DuckDB answered in 3 milliseconds. Spark took 154 milliseconds, 50 times longer than DuckDB, measured on this machine. Now give both engines 100 million rows of that same table, and the gap falls to 5.5 times. Spark did not get faster. The job got big enough for the useful work to start paying back what Spark spends on planning, coordination, and moving data. So where did that 154 milliseconds go? Almost none of it was reading 1,000 rows. Spark planned the query, decided how to divide it, asked for 200 partitions, and coalesced them back down, launched 4 tasks, wrote 1.4 kilobytes of shuffle files to disk, and collected the answer back to the driver. Every one of those steps happens whether the table holds 1,000 rows or 100 million rows. Subscribe if you want the mechanism instead of the slogan. DuckDB skipped all of it. It never left the process it was already in. A benchmark run on a workload that small is never measuring the engines. It is measuring their fixed cost, and it always exaggerates in the same direction. Here is the bill. Total time is useful work, plus execution overhead, plus data movement, plus coordination. Planning and scheduling put a floor under every job. The other 2 terms are not fixed. Data movement scales with what your query redistributes, and coordination scales with the partitions and tasks that takes. On a tiny job, the floor is the whole bill. On a big one, useful work grows until it dominates, and the small-end ratio stops being true. There is one number I have kept out of every comparison. Starting the Spark session on this machine took about 4 seconds. None of the figures you have seen included, because timing a warm engine against a cold one and calling the difference an engine law is the oldest trick here. And it depends where you run. That 4 seconds is local mode, paid once, and on a warehouse that is already running you do not pay it per query. But if your job is a small one that fires every few minutes, startup is not a footnote. It is most of your latency. Watch the ratio move. Counting requests by endpoint. DuckDB against Spark at 1,000 rows is 50 times. At 1,000,000 rows it is 11.5 times. At 100 million rows it is 5.5 times. Between the last 2 measured points, 10 million rows and 100 million, the ratio was roughly flat. The query and settings stayed the same. The workload grew, changing both useful work and the execution costs around it. Your own crossover sits somewhere on a curve like this one, and where it sits is a property of your workload, not of the 2 logos. Now change the query instead of the data. Same 100 million rows, same files, same engine. Group by endpoint, and Spark moves 17 kilobytes between its stages. Group by the user column instead, and it moves 131 megabytes. Same rows, 1 line of SQL different. Spark's documentation calls the shuffle a complex and costly operation, involving disk, serialization, and network, and that is the line item your 2 queries disagree about. On the clock, the second one costs Spark 9.5 times the first. Whatever rule of thumb you carry about data size, it has no term for this. That movement happens at a boundary. Spark's glossary is plain. A job is divided into dependent stages, and a task is a unit of work for one executor. The stage that reads those 131 megabytes cannot start until the stage writing them has finished every task of it. That waiting is the coordination term in your bill. More executors let Spark run more tasks at once. They do not move the point where everything has to line up before anything continues. DuckDB has blocking operators of its own. What it avoids here is Spark's distributed stage scheduling and its cross-executor shuffle boundary. That heavier query has its own curve, and it is steeper at both ends. At 1,000,000 rows, Spark took 2.3 seconds against DuckDB's 67 milliseconds, 34 times. At 10 million rows, 7.7 times. At 100 million rows, 3 times. The engine that looked hopeless at the small end is within a factor of 3 at the big end, on a single laptop, on the workload that suits it least. Nothing here says Spark takes the lead if you keep going. It says the number you would have quoted from the small end was never a property of the engines. Here is the same measurement read the other way around, and it should change your decision. Going from 1,000,000 rows to 100 million rows on that heavy query is 100 times the data. DuckDB's time grew nearly 45 times. Spark's grew under 4 times. DuckDB was still faster at every point I measured, including the last one. What changed is the size of the gap, and this benchmark does not tell you where, or whether, the two curves cross. Which is why the useful question is not which engine is quicker today. It is how much of your build does not shrink. So why is the single node path so quick? DuckDB runs inside your Python process. Its documentation describes a columnar vectorized execution engine that processes a batch of values per operation, and it parallelizes across your cores with morsel-driven parallelism. Nothing crosses a process boundary to be counted. And one thing that is easy to get wrong. DuckDB parallelizes a parquet scan across row groups, so the available scan parallelism depends on how the file was written. I measured these files. The file with 1,000,000 rows in it is one row group. The one with 100 million rows is 25 of them. The part a laptop cannot measure. Everything you have seen measures what distribution costs. None of it measures what distribution buys. Spark's docs are specific. A resilient distributed dataset is partitioned across the nodes of a cluster. It automatically recovers from node failures, and a lost partition is recomputed from the transformations that created it. A cluster manager allocates resources across applications. Spark schedules concurrent jobs inside one. On one machine, there is no node to lose, no cluster to spread across, and one query at a time. That is the case that flatters a single node engine most, and it is what I measured. The ceiling on the other side is in DuckDB's own docs. Larger than memory processing is supported for grouping, joins, ordering, and windowing, so the idea that it all has to fit in memory is out of date. But the same page warns that several blocking operators in one query can still run out of memory. The memory limit you set covers the buffer manager, not every structure in the process. And one machine is one failure domain. If it dies, the query in flight is lost. There is no second node, and no distributed partition recovery to carry it on. You rerun it. So here are two shapes, and they are illustrations, not measurements. First, a few gigabytes of parquet sitting on the machine you are already on, one analyst, a filter, and an aggregate, nothing that has to survive a machine dying. A single node engine may finish before the distributed overhead is repaid. Second, the working set does not fit on one machine, where the data already lives across a cluster, or 40 people are querying it at once, or the pipeline has to recover when a node disappears. Now the coordination you were paying for is the product, which is the number you came for, and it does not exist. There is no row count and no file size that separates the two. Your crossover moves with your hardware, your file format and compression, the shape of your query, what is already in page cache, where the data is stored and what it costs to pull in, your Spark configuration, whether the cluster is already warm, your network, how many people are querying at once, and the version of both engines. The two numbers I measured on the same rows differed by 9.5 times, and only the query changed. So the rule, and it is a question, not a threshold. Before you reach for a cluster, ask how much useful parallel work this job actually contains, and whether that is bigger than the cost of dividing it up, moving it around, and waiting for it to come back. Ask what your query has to move, not just what your table weighs. Ask where the data already lives, how many people need it at once, and what happens when a machine dies. If the honest answers are small, local, one person, and nothing, then one machine will usually win, and choosing it is not a downgrade. If the answers are large, distributed, many, and something has to survive, then coordination is not the overhead. It is the thing you are paying for.